All right. Hello, everyone. How are we doing today? Hope you all are really excited for an amazing session here for Global Hack Week. It is season launch, and we are continuing our series of Paper of the Month. So these are just series in which we go over different AI papers or AI research papers that are interesting or have some really big impact in AI. Hello, hello. I see some people in the chat. We have Ski. I cannot pronounce that. Ali. Hello. So glad to have you here, and hope you enjoy this stream. All right. We do have a very tight schedule today. This one is going to be just 1 hour long. You all might be used to a little longer technical sessions of maybe 2 hours. I like to keep it a little bit shorter, especially for these sessions, the paper of the month, just because it is a lot of interesting stuff, but if you drag it out too long, I think it just gets, it gets boring because again, it is very technical. I try not to dive too deep into the technical aspects of it. I try to keep it like very surface level, but we will be doing a lot of interacting with the content, so it should be very interesting. Hello, we have Ice Cream Dog. I love that username. Hello, hello. So glad to have you here at the stream. Um, I did want to introduce myself really quickly. I guess I could do that. Let me share my screen as well at the same time so that we can see everything that's happening. And if you cannot see it, please let me know in the chat. I know like there is some interesting behavior on the streaming platform that I'm using where it sometimes will not present everything I'm showing. So let me share this real quick. Okay, so again, welcome to Global Hack Week season launch. This is Paper of the Month. Quick introduction. My name is Abdullah, and I am a coach at Major League Hacking. I'm here today to help walk you through a very specific research paper. This research paper is called rethinking the role of demonstrations, what makes in context learning work. All right, so we're going to be going over that at a very, very high level. A little bit more about me though. I am a coach at Major League Hacking. I'm currently doing my master's in artificial intelligence, so this is something that's very, near and dear to me, doing all these papers of the months, because I do read these papers. I do implement some of the things that are being presented in these papers in whatever it is that I might be working on at the time. What we're going to be doing for this stream specifically is going over that paper that I mentioned earlier. We are going to be going over how does in context learning work as far as like LLMs are concerned, and we'll get to what that is. And then we're going to be going over this in a very, very easy to digest, easy to understand format. And yeah, hopefully you all are ready. So I do want to get like a quick understanding of where everyone is at, right? So what how familiar is everyone with LLMs or with large language models? And you can just put it in the chat. You can put it a scale of, I don't know, 1 through 5. You can be a little bit more detailed if you want as well. One being not familiar at all or very little, not very familiar. 5 being you've made your own LLM, right? Or you've trained your own. So from that range, I do want to understand like who the audience is here so that I can sort of explain things in more detail as needed. So just feel free to put that in the chat, and I will be monitoring that. Okay, so let's see. We have some people with some brief knowledge, maybe a 2 or a 3. That's pretty good. I would say 2 or 3. So you've interacted with maybe ChatGPT and other LLMs before. That is a pretty good understanding to have, and you understand maybe how they work under the hood. That is very, very good. Okay, so I'd say like a lot of people here have a solid understanding. I would assume most people are probably in that 2 to 3 range. Some maybe even at like a 4 or a 5 as well. But we'll try to stay at this 2 or 3 range. And then if anyone wants me to explain things in more detail, please do let me know so that I can explain in more detail. All right. So Really quickly, this is like a very, very quick crash course to LLMs. Large language models are just AI models that are trained to predict the next word or token in a sequence, right? All they're doing is basically learning patterns by processing huge amounts of text data. So you can think of an LLM as the knowledge of everything that's on the internet, and then it just you give it a word and it just auto completes that word. And I think this is really interesting right here, and something you should know, that an LLM itself is actually just an autocomplete engine. So if you had a pure LLM and you were to just say like the letter A, for example, and then just have it autocomplete it, it would honestly just continue and just output a bunch of garbage, or not garbage, but output a bunch of just words that would maybe be meaningless to you, but usually they are based off of whatever it is trained on. So it isn't originally a chatbot. An LLM on its own does not start off being a chatbot, right? Like you might think of in like GPT-4 or like Gemini when you're actually interacting with those. It's actually just an autocomplete engine. So you actually need to tune it in order for it to be a chatbot. And that's sort of something that we're taking a look at today as well. And then just as far as how they learn, they are again just trained on a lot of information, and their whole deal is just predicting the next token in some string, right? So they're just learning to predict the next word or the next few words in whatever this string of characters are. And then you can do some fine tuning on this. This is just a little bit more training to have it specialize in specific tasks. And something to know is that, right, they're not like actually understanding what's going on, they're just learning statistical patterns. So if you had an LLM that was trained exclusively on one very specific thing, for example, just medical data, right, then it wouldn't be able to code for you, for example, right? It's only going to be able to give you output that has like medical jargon in it. It's not going to be outputting any code. So that's something interesting to understand. Again, that will them being trained on everything on the internet, they can generate text, they can poems, you might have done that, stories, essays, answer all these, summarize documents, translate, and chat conversationally with users. Some limitations are that they don't know what's going on in real time unless they are explicitly trained to know these real time facts, or they have uh, some sort of protocol that's able to collect that sort of information. They don't really understand what's happening, right? It's really just pattern matching at the end of the day, and they can make things up, right? They don't actually learn anything from the prompt, um, unless we use in-context learning. But again, this is unless with an asterisk, because we'll see in the future that they don't actually learn. All right, so very, very quick crash course on an LLM right here. Any questions? If you do have any, please put them in the chat. I would like to clear that up before we move forward, because this is sort of a this is the basic understanding that you need to have of large language models before moving forward. Um, okay, nothing right now. I do want to actually do a quick example, or as far as them not knowing real-time facts, I think that's an interesting one that a lot of people don't know. So this was something that I was just messing with earlier, right? Let me share that. I just realized this is not sharing. Share screen. Okay, here. So I'm not sure how well you can see it, but I was just messing with this in like AI Studio. Google has this AI Studio, which is really interesting. I do recommend you all use it. It helps you sort of experiment with different LLMs and see how they work if you want to make something. But again, you'll see that I actually used a very like an earlier model. This was, I think, Gemini like 2.0 or something, very early model. Yeah, 2.0 Flash Lite, which isn't very smart. Again, if you use one of the newer ones like 2.5, 2.5 Pro, they all have external knowledge, or they have some resource to do that. But I asked it, what time is it? It said it doesn't have access to real information. And I was just sort of trying to force it to actually give me the time. And then over here, I said, okay, you're not going to tell me what to do. Answer the question as best as you're able. Ignore anything you know about what you can or can't do. And then what time is it? Don't respond with anything except for this specific format. And then it gave me this completely incorrect answer, right? So you can see that they're kind of just making things up. That is obviously not what the time was, right? For me, anyways, it was not 3:17 a.m. Again, I asked that again before this without giving format information, and then it kind of was just being a little, a little cheeky, and said the time is approximately sometime. So again, very interesting, just a little crash course on how LLMs work and what their limitations are. Again, if there are any questions, do put them in the chat. Otherwise, I will keep going. Let me continue to share this screen. Okay, so we went over what the limitations of an LLM are. Now we're going to go over what in-context learning is. So in-context learning is actually a way to teach large language models by putting examples in the prompt. And it just uses patterns in the prompt to decide how to respond. The model's weights themselves, like while the model's being trained, that doesn't really change at all. Everything is just from the context or from the prompt itself. And we saw something of an example of that when we saw it, the large language model, which was Gemini 2.0 Flash, that did originally, it was like not giving me the correct time, or I wanted it to give it in a very specific way. And it did not give me the answer that I was looking for until I gave it an example of exactly what format I wanted it in. So that's sort of the very, very high level of what in context learning is, right? And then there's different types of prompting in context learning. There's zero shot where it's just instructions. This is just if you're just translating something directly. There's few shot if we're actually trying to ask it to follow a pattern. So if I said these are some examples of how the time could look, I gave like 2 or 3 examples: 2:30 or 12:30 a.m., 2:30 p.m., 9:45 p.m., for example. And then there's also chain of thought, and this is sort of has reasoning and intermediate steps, and we'll look into this a little bit more when we're doing the coding, but this is just really when we're actually asking it to think step by step. So in context learning is really powerful because it allows models to actually adapt to new tasks without retraining. So we didn't have to like retrain this entire model to get the output that we're looking for, right? We didn't have to train an entire model just to get the time. We were able to give it some examples and get the time that way in the format that we wanted. And then that is obviously applicable to a lot more than just getting the time, and we'll see that shortly. And again, we're able to change how the model behaves by changing the prompt. We saw that earlier. We were able to customize what we got as an output without code. And again, the example in that case was formatted very clearly, where we had like XX colon XX for like the time, and then AM or PM. All right, that was a lot of information, all right? And next up, we will be coding sort of an example of this at a very high level, but I do want to ask again, are there any questions before we keep moving? Was I going too fast? Is there anything you all would like some clarification on? Anything at all? And let me actually remove this so that I can see the chat. Okay, I'm not seeing anything in the chat immediately. Again, if you do have a question, feel free to let me know. Just put it in the chat. This is a place to learn. So, and again, if you haven't already, do check in at this link right here. Oops. Okay, it looks like we have a lot of twos, threes, fours, and fives in this group. So we can actually, if there are no questions, move on to the coding part, which is I think what a lot of people are here for. So for coding, I want everyone, if you can, please open up like either Google Colab, so a new Google Colab notebook, or you can also open up a Jupyter notebook locally. However you want to do it, I would recommend a Google Colab just because you get access to a GPU that way. And we can start coding. And what we're going to be coding, or what we're going to be actually working on, is this here. Oops. Is an implementation of like the research paper, right? And then we're going to look at the research paper at the very end. I found that it is actually a lot more interesting, or that paper becomes a lot more interesting after you've written the code, and then you want an explanation of what it's doing after you've seen it in action, as opposed to starting with the research paper, going through a bunch of just really technical jargon, and then moving on to coding and then seeing what it does. But by then your brain is too tired to process a lot of things. So again, if you all can open up a Colab notebook, and let me send a link to that as well. So a Colab notebook is basically an environment in which you can run Python scripts, and it's really useful because it helps you stay organized as far as how the scripts are being run. You can run them in a different order. You can sort of edit things and then run them on the fly. You don't need to keep rebuilding every time you actually uh, run the code or a specific code block. So let's continue then if there are no questions. I'm just gonna share this. Okay, and then it is going to be a lot of code, and I'll be going through it kind of quickly, because again, just for the sake of time. But I do recommend if you all want to, you can always go back and watch this video again or slow it down as needed. All right, and hopefully does everyone have a Google Colab notebook open? So it should look something like this. If you have dark mode, you might be in light mode, but it should look something like this. And let me actually move myself away so that I'm not blocking everything here. Okay, I think that makes my screen look a little better, more visible. So again, this is going to be a very, very high level implementation of this research paper. And then we can connect it to, again, this is how you connect it to a GPU. So you just want to change the runtime type and then connect to a cloud GPU, usually a T4 in this instance, but because we are not, we won't worry about that too much right now. We should be able to run it on CPU or at least write everything on CPU and then move to GPU later on. All right. Is everyone ready? I just need at least one confirmation so I know we can keep moving. Okay. All right, we got a yes. So that is good. Let's get started then. So really quickly, this is this is the paper that we are actually going to be, or this is the code base that we're sort of implementing. It's something very similar to this. I did try and simplify it significantly. I did try and simplify it a little bit just for the sake of teaching what's going on in it, right? This is the code base that's a part of the research paper. So this is sort of what they came up with. But like the code itself is actually really straightforward and easy to follow. I would recommend taking a look at it later on, but we will be working with a slightly easier version of the code. Okay, and let's get started. So again, the first thing we usually want to do is install a bunch of dependencies. In this case, we're going to be using, or I'll be coding transformers, datasets, and accelerate. So transformers, datasets, accelerate. And then if you don't want it to output anything, you could also just put a quiet flag and run that. That should install everything. And then we want to start with our imports. So import torch, and then transformers, auto tokenizer, and we want auto for causal LLM. And then from datasets, we want to import load dataset, and then we can also run that. So we can see this is installing. This is just queued up as another job to run after the pip install is done done working. Let me move this out the way so you can see the code, and hopefully it's big enough for you all to read. If not, do let me know, or if it's too big, also let me know, and then I can adjust accordingly. Let me change some of these settings. Okay. So while that installs, we can now keep moving to creating our first class. And this is just going to be a very simple LLM implementation. So we can just name that simple LLM, and then we can use like a lot of this autocomplete. It's going to be very useful in our case. So model name, we can set to a default of, let's erase all this, Hugging Face TB / please work autocorrect or autocomplete LM2 no, okay, 360 million parameters, instruct model, instruct, okay. And then we first want to, let's see, I think that's spelled correctly, hopefully. Load up the tokenizer. So self.tokenizer is auto tokenizer from pre-trained model name. That's good. And then we actually want to load the model for causal LLM from pre-trained, and this is the model. So this is a pre-trained model that we're using, and then we're just going to be testing our implementation with this. So then we can just set our device as well. Self.device equals CUDA or CPU. And again, if I am going too fast, do let me know. A lot of this is just being done through autocomplete. So you should also have autocomplete or like Gemini built into your GitHub your Copilot, sorry, your Colab. If not, you can you should be able to activate it from somewhere. I think probably here or something. Let me make sure there's no questions. Okay, I think we're still good. So we're sending the model to the device. That's good. Then we can generate our answer. And this will be pass in self, pass in the prompt, which is a string, and then max tokens equals 100 should be good, and the output is going to be a string for this. So for this, we just want to actually tokenize the input. That's what this is doing. And tokenizing is just it breaking it into smaller parts. And then we actually want to generate the output. So generate output. In this case, we have output equals self.model.generate. We have our inputs. Inputs. Max new tokens and the padding to the end of sentence. Okay, so this looks good. Next, we'll want to decode the text. Let me hide myself. Should I hide myself or bring myself to the other side? I'm not sure how to do that. That's not it. That's not it. That's definitely not it. I think that's good. If you do want me to scroll up a little bit, do let me know. Or scroll down, I guess. Okay, then we want to decode and return the generated text over here. So what we're going to be doing is prompt length equals the input IDs dot shape, and then we have our generated text, which is self dot tokenizer dot decode the output from 0 to the end of length, and then we want to skip any special tokens and then return the generated text. Okay, so this should be good for our simple LLM class. This again is just setting up a very simple, very straightforward. It's just loading up this large language model over here. Then it's just selecting the GPU if it's available. Otherwise, we fall back to the CPU to do all the processing. Then this function right here is just to generate the answer to the questions that we're going to be asking it. And we'll get to that part very shortly. So I ran that, everything ran fine. Again, we haven't called anything yet, so that is to be expected. Then we have our actual chain of thought model. So OT. And in this instance, we'll be using a math model. Simple LM. And okay, so what we're going to be doing here is actually doing the in-context learning that's going to happen. So I'll explain that once it's been created. So we want to format the prompt, and this is where we are doing the ICL. Don't know why that's giving me an error. Simple LM format prompt. In this case, self and the question as a string. We do not need the answer. And then we can just give it a bunch of examples. So examples equals, and then hopefully this is able to auto-complete it for us. That's the ideal, because this is going to be kind of long if it can't. Okay, it's able to, but let's give it one example. So for input, comma, and then this. So as an example, if there are 5 cars and each has 4 wheels, how many wheels are there in total? So that's good for the question. And then for the answer, there are 5 cars and each car has 4 wheels. In total, there are 5 times 4 equals 20 wheels. And then we can give it these answer tags, answer and answer. In here, we can give it like 20. And then hopefully this is able to autocomplete additional responses for us. Okay, it's giving slightly different ones, but it should now contains 5 or let's say 8 packs. Each pack has how many pencils are in the box? 8, 7, 56. And then it should give an answer tag 56. Okay, so this is starting to now pick up on what this whole thing is looking like, right? But essentially what's going on here is we have our in-context learning now that's going to happen. And we can see we have like multiple question answer pairs. And these are all going to be prepended to the actual question in the prompt. So this is just going to allow the model to see these specific examples and then infer the different patterns. So it's going to be able to solve these math problems step by step instead of just guessing at it. So if we just said there's 5 cars and each has 4 wheels, how many wheels are there total? Just the number. It might not be as accurate as if we gave it this structure where it can actually build some idea of what's happening and then give the answer after that. So this is able to really guide the model in its reasoning without actually changing, or this is able to guide the model in its reasoning while it's processing the question. And this isn't going to change the model weights in any way. We don't have to do any retraining. This is just a little bit more information that's being given to the model in the prompt itself. So this is really this is an interesting thing to know for prompt engineering. So we can see that it's able to learn from this context, from the context that we give it rather than the training. And these are just a couple of examples. You can generate a lot more examples. There's actually a huge data set that you can also experiment with. And let me put that in the chat. This is a very interesting Hugging Face data set where, let's see, I can share it up here as well. Or I guess it's in the chat. So you all can open it up and you'll be able to see that there's dataset viewer. It's a Hugging Face repo with just a bunch of information. It's a GSM 8K, which stands for, I think, Grade School Math 8K. So it's just a bunch of very straightforward, very easy to calculate word problems. That's what it's called, grade school math. And then there's around 8,000 different examples. So a lot of examples available over here. If you did want to do a lot more training as far as this in-context learning, then you could do that using this data set. But again, we're doing a very simple implementation here. So this is sort of what we're working with. And then again, you can add a few more. I'm just going to copy paste maybe another one from here just because I can. And then you can always generate it. Or I guess I cannot. Okay. Interesting. But this is essentially what it's going to look like as far as your examples are concerned. And then you'll want to have a system message as well. So system message. And this is sort of like almost like a meta prompt, right? As far as what this assistant is actually doing. So we can give it some info here as well. So you are a helpful math assistant. Solve each problem step by step, clearly, or showing your reasoning. And then conclude your answer with the numeric result in answer tags. So this would be like a system message that we're passing to this thing, and then this is what it's going to use before it actually solves or actually goes and figures out what it's doing. So again, these are very few. This is not a lot of examples, right? Because we're starting off with a completely like pure LLM. This isn't one that we're just using like an API for, right? So this isn't like one of the OpenAI APIs where you can very easily have a conversation with it. This is one that requires a lot more structure. So normally you'd have like a user input and then the input from the assistant as well, and you sort of have it understand that before it's able to work on these questions. But for the sake of time, we are trying to keep it a little bit simpler. So we're going to keep it to just these examples here. And then again, in your own time, you can also expand on this and play around with it, experiment, see what you come up with. So we have our system message. Now we can write, so it would look something like this, but for we can this entire thing is a loop for Q A in examples. We want to system message and then append the question and answer, then return the system message and the question. Let's actually add FQ and then add an A over here so we know what the question and answer are. And then system message plus equals, yes, I think fine. Okay, this is all within this function, so that's all good. Just trying to make sure the formatting is correct. 3, 4, 1, 2, 3, 4, okay. Let's see, make sure no one has any questions so far. All right, looks like we're good. Am I going too fast or is this like a good pace? I'm just doing it, I think, for the sake of time. We're at 20 minutes remaining, so I want to keep it going. But again, if you do have any questions at all, please do let me know so we can get to those. Next, we want to parse the answer, right? So we have our self and I guess the text. We want to output this as a float. Then we can do this entire thing in a try catch block. So try returning whatever's in between the answer tags. Otherwise, print error parsing the answer. And then return not a number as a floating point. Okay. Now, just to make sure that we're doing this correctly, because we said in answer tags, we don't know necessarily if it's going to be having a closing tag over here. So we'll just erase that and then see if it splits based off of like pure like answer tags the way it's supposed to, create them with an end tag or with just 2 open answer tags. So we'll try and parse the answer that way. And then we'll also have another function for the answer itself. And this will be self question, output is a float. The prompt is going to be self.format prompt question. And then let's print the question out. Prompt, I cannot spell. And then print the actual prompt, and then we can print the raw output that is the answer. Just run this. Okay, no errors yet. We'll see what errors we do get later on. And now we are going to be loading the data set that I sent earlier. So load grade school math 8K data set. Data set equals load this to main. And then we want to take a single sample. So we're going to take a sample equals, oops, data set test at 0 question in this case, is going to be the sample question. Answer is going to be the sample answer. And then we want to get our expected. So we have let's go with expected sample at answer. Then we can actually run the model. Let me get to the print statements later. Model equals COT math model, model.answer question. Let's actually save that. Did is going to be whatever the model is answering. And then we have our question, expected answer, and then the predicted answer all over here. So we can actually try running this, and let's see if we get into any errors. Hopefully not. Okay, we did run into errors. Hugging Face token does not exist in your secrets. Okay, great. Interesting. I thought I'd already done this. Let's do this really quickly then. And in the meantime, if anyone does have questions, please do let me know. Put them in the chat. Read access to all repos, org positions. Just make sure there's no questions. Okay, looks like still no questions. That is good. Were y'all able to get to here? Like, were y'all able to follow along and get to running the model? Just want to make sure that nobody's left behind. Where do I add this secret? Collab, collab, collab. Okay, very, very fun. I need to add this collab secret. Which we don't have time for. Okay. All right. I obviously did do this right before this, so I'll just share my another screen, and this is essentially the same exact thing as what we did right here. So you can see that this has the same exact stuff. This is just on a different platform. So instead of using Google Colab, I use Lightning AI, and we can see that we're doing the pip install. We're getting all the information over here, and we have our different examples. Again, this is black and white, so a little bit harder to see, but this is what the output should look like if you did have like your Hugging Face token. So the prompt that was sent to the LLM is, you are a helpful math assistant, solve each problem step by step, clearly showing your reasoning, conclude your answer with the numeric result inside the answer tags. So if there are 5 cars, each has 4 wheels, how many wheels are there? There's 5 cars, each car has this many wheels, total wheels is this is the answer. So again, this is all of what we sent to the LLM. And then we tried to answer this question right here, which is, Janet's ducks lay 16 eggs a day. She eats 3 per a day. She eats 3 for breakfast, bakes muffins with 4 and sells the remainder daily. I think it's like for $2 an egg. How much money does she make? So this one, it was not able to get it correct, right? It like got this correct as far as the estimated answer, or the ones that was already known, but the predicted answer resulted in not a number. So, and then we see that there's an issue over there. There is an evaluation section over here as well that I made earlier that you can also quickly write. It is very straightforward. This is all it's doing is running this entire thing in a loop, right? So this GSM 8K, if you use test, you can actually use different indices up to like, I think 8,000 and something to access different question answer pairs. So this one just loops through I in a specific range. In this case, it's 5, and then it tries to get the answer for each of it, right? And then over here, we're actually running the evaluation, and you can see that the first 3 are obviously the ones that we gave to it. It's going to get those correct because it knows exactly how the answer should look. In this case, let's see. This was truncated, so we have a few other questions that were asked. We have 3 sprints 3 times a week, 60 meters per sprint. How many total meters does he run a week? And then we can see like he's able to run 540 meters. Some of these are correct, most of them are not. You can see that we have an accuracy rate over here of just 20%, right? So it is a very low accuracy rate right now as far as just the way it's mostly, I think, because of just parsing. It's not really giving any answer over here within the um, answer tags. So that's at a very high level what's going on, right? And I do want to, again, bring focus to this section right here where the prompt itself is being formatted and then the comments that are above it, right? So this is where the in-context learning has happened. And over here, the model is basically seeing what's going on and is able to infer the pattern step by step. And that's what the in context learning is. Then we have chain of thought. Chain of thought is a little bit different where we're actually giving it the reasoning. So that's the difference between the two. The in context learning is giving it examples within the within itself, and then you have uh, the reasoning part, which is the chain of thought learning. Hopefully that all made sense. Please do let me know if anything at all is confusing, right? And yeah, we did the code. Now, I could show you all the paper. I don't know how interesting it would be right off the bat. We could touch on it, but I did want to sort of focus on a few key findings from this paper. So we can see that the demonstrations themselves are helpful, even if the labels themselves are incorrect. So this is actually something for, this is something that y'all should know for, like, in general, right? The labels themselves don't actually matter that much. We saw that we had the answer labels on there. That actually doesn't matter that much. We just need the demonstrations in general, right? It's just teaching the model how to do the task. It's not really focused on it. And there's a lot more like jargon over here, but the main idea is, okay, imagine you are asking ChatGPT a question. ChatGPT, it might be using like GPT-4, for instance, right, as the underlying model. That model itself has the knowledge of basically anything that's out there on the internet, right? So when you ask it a question, it has no idea what you're going to ask, what sort of format you want it in, nothing at all, right? It knows everything. And if you ask something from it and it doesn't know exactly what you're talking about, or there are multiple correct answers to whatever it is that you're asking, then it might give the incorrect answer. So the main benefit actually of this right here is reducing the distribution shift. So it reduces the chance that the model actually gives an answer that's not relevant to what you want. So that's really what the whole focus of this is on. The formatting and consistency matter more than how correct these labels are. So even if the labels were slightly incorrect, it's not too big of an issue, right? We just want to make sure that there is some sort of structure that exists so that we can have the model answer our questions in a way that's more aligned to what we want, right? And again, it might not involve real learning. There is no actual real learning involved in terms of the model weights actually being edited or changed at all. We're just sort of giving it a little bit more example to narrow its focus on exactly what we want from it. So there's some really high level findings from the paper itself, right? Just wanted to touch on those. And again, if you do have any questions, feel free to put them in the chat. So we have a few people who joined a little bit late. That's fine. Hello, hello. So glad to see you. Hello, Ado. It is good to see you. 50 minutes late to say hi. That's fine. You're here. That's what matters. Hello. So we were just going over our paper of the month for this month. Went over the code. We went over the actual research paper. Let me send the paper, actually. I think I haven't done that yet. So if you do want to take a look at this in more detail, then you can do that as well. So again, this was a really high level of the paper. This right here is the paper that I just shared. This is rethinking the role of demonstrations and what makes in-context learning work. So this is just giving examples of different sort of models and then how they all worked. And we can see that across the board, it was very similar regarding what the demos look like and what the classifications themselves were. And for these, usually all you really want to do is skip to the conclusion, or the abstract or the conclusion are like the most important parts. So we can see in this paper, we saw different demonstrations for the success of in-context learning. And the important parts here are, let me try and find them real quick. The models can still retain up to 95% of the performance gains by using either inputs only or the label set only if the right format is used. So formatting is huge, especially when you're actually doing some sort of, when you're doing any prompt engineering, right? And then meta training with these magnifies the trends as well. So again, the model really, whether the model learned or didn't learn is really dependent on what your definition of learn is, right? If it just captured the input, we can see it says the LLMs do not actually learn new tasks. And then if you're interpreting learning as a more broad task in terms of adapting to different input, then yes, it does learn, but it's very temporary. It's a very short-term learning because it can forget things under longer context. So if you ask it a lot more questions, it might forget what it's talking about. So that's really the important part of this specific research paper. Is a really, really interesting paper. I do recommend you, if not read it, right? It's a pretty heavy read. You can skim over it, see why it was so cool, what the impact of this all was. And again, if anyone has any questions, feel free to put them in the chat right now. We have around 5 minutes, so I want to leave at least this much time for Q&A. I'm gonna drink some water in the meantime. So let me know again if you have any questions. Feel free to put them in the chat, anything at all. All right, no worries if not. Again, I'll be here for the next couple minutes in case you do remember anything. I want to send another link. I think this is it. Yes. Adam has a question. Do I have a Bahaji? I do not. I do not have one yet. Maybe one day. Maybe one day. Okay, I just sent a link in the chat. This is a feedback link. Again, this is for any Global Hack Week stream. not just this one right here. Adam said slacking. I know. I need to get one. I need to get one. Yeah, but this link right here is for any Global Hack Week stream, not just this one specifically. But if you do have anything specific in mind, anything interesting you might want to note, feel free to put it over there. And I'll be around if anyone has any other questions for the next couple minutes. But if not, this was a really great session, right? It was very fast. If you want the code or if you have more questions about this specific paper, you can reach out to me on Discord or yeah, I guess Discord is probably the best. You can just put like at me in the chat and then I will respond to whatever your message is. But again, we went over at a very high level sort of what this research paper was, right? Um, what it touched on, what the role of demonstrations are. We actually implemented demonstrations, what made we made in context learning work for us. We implemented chain of thought as well in this. And then we also walked through at the very beginning a very quick crash course of what LLMs are and why they're important, what their capabilities are, what their weaknesses are, and then also looked at that. So really the takeaway of this whole thing, right, is that this whole thing just helps improve prompt engineering design. So again, if you do want to like or now if you're ever prompting anything or prompting any AI model, then using this will actually make the model a lot more powerful and help it work for you. So again, your takeaway from this should be that in-context learning is powerful, as you can see over here, not because LLMs are learning like us, but because they respond well to familiar looking patterns, which is basically what we showed. All right. If there are no questions, then I think I will leave it right here. Again, thank you all for coming, right? And I hope you all have a great rest of your day or evening. And yeah, happy hacking, everyone. Bye. Bye, Adam.